So I think we will now move again from optics to matter, so to really particle that has a mass and a weight. So as Bill said, I mean, I'm also part of this community to be atomic physicist, and I thought I really would like to take the opportunity to say what I think it's one of the things really fascinating atomic physicists. And so if you think about, so there is a great world of opportunity in a single atom. So a single atom was one of these incredible objects that has seeded the fundamental new theories. So by shining light on a single atom, it was, for example, discovered that there is orbit around which the electrons are moving, that the energy actually is quantized. And this is really one of the key fundamental discoveries in quantum physics. And so you have actually the ground state, so the lowest energy level, and then you have the next excited state. And the observation of this line of energy was kind of at the foundation of the law of quantum mechanics. But then not only the observation of line, you could say, okay, now I take another atom, which is a little bit more complex, and what I discovered that there are more energy line than what we were expecting. And this was seeding another big discovery that is really the law, the statistical law that governs the behavior of particles. So it was discovered that there is an intrinsic, let's say, properties that the atom has that are connected with the so-called spin. But also we can go even further, and is about not only how many lines one single atom has, but also the exact energy difference between these lines. And we could look at very tiny shift, and there was very specific shift that push us to really think about what is the notion of vacuum, which I think it's a very intriguing, let's say, concept in quantum physics. And so it was inspiring new theory, which we're calling quantum electrodynamics. And this is all the power that you can have in one atom, and that's why sometimes we think that the single atom, and hydrogen in particular, was the Rosetta Stone of two quantum possibilities. And this quantum possibility, we already learn and heard something about it, because of course if you have now two energy level and one atom can oscillate up and down, it's kind of making a clock, and the clock can be extremely sensitive, as was pointed by Emmanuel Bloch and by Bill Phillips. But also we can start to not think anymore binary, in the sense either one atom is in the low energy or is in the high energy, might maybe be simultaneously in both of them, and that's really the idea of the superposition. From this, we move to the entanglement, or this key concept that Anton was introducing. And all these are really power which are thinking about a single atom. Now imagine if I don't have a single atom, but I suddenly have two atoms. Now there is things which are very relevant, because of course not only every single atom are kind of enjoying this concept of particle wave duality, in which at the same time you can describe an atom like a wave function and in terms of probability, but this can also overlap between themselves. And so these open new doors of possibility. And also if you have more than one object, no matter which type of object, they can interact between them. And now if you don't have two, but you start to have more and more and more, so what you can, and each of these you can imagine to be little wave, and this wave maybe can interfere and can interfere constructively. What you are creating is a new phase of matter, which is really purely quantum mechanically, what we call Bose-Einstein condensate. So suddenly you are able at the macroscopic level of many particles to measure, let's say, quantum phenomena. And in terms of interaction, there are actually two types of interaction. One which is local, so it's really all our quantum particles, which should be extremely cold. Also here is the kind of price to pay. They can interact when they are close by, and so those is the contact type of interaction is a billiard ball type, but neutral particle can also have long-range interaction, like little magnets that interact with each other. And that's extremely relevant because long-range interaction is the essence of main interaction really existing in nature, if you think about. And you need to have for these very special atomic species, which are very magnetic, such that the magnetic interaction is very big. And so this is an example that go back to what Emmanuel, let's say, was pointing out, is that you can create this simulation, you can initialize a system of many of such magnets in kind of a crystal made of light, and then what you can do is to do this quantum simulation in which now you are switching on a strong connectivity between the particles. But now let's forget one moment about the crystal of light or ordering atom. What happens if you don't do that and you simply have many, many atoms all in the quantum regime, so they are all interfering to each other, and which are interacting with magnetic interaction. And now something new is happening because you have now a system which have new ingredient in a way. And so you can realize yet with this system a new paradox of quantum science. And so we heard about, you know, this idea of the Schrödinger cat, which is in a way paradoxical in the way sometimes we describe it, because the cat can be dead and alive at the same time, so the particle can be particle and wave at the same time. So this kind of idea of being two things at the same time is extremely powerful, and is kind of an essence in a way of quantum physics. But if you, let's say, you can push this idea to the state with many atoms, and then, for example, you can create a new state of matter that can maybe be superfluid, so have some fluid properties without viscosity, and crystal property at the same time. And this is, again, a new type of state that you can create. And so that's now a picture that you can realize in the lab using magnetic atom. And I think it's very relevant because you need to imagine that you can measure and create a state which is a gas. Atoms are kind of flowing in this state without any friction, having fluid properties. And at the same time, the gas itself organizes in space like making a crystal. So it's this kind of very strange even to imagine how a state can have, let's say, the rigidity of a crystal, the fluidity of a superfluid, and be in the gas phase. And those are really, let's say, pushing even more some concept of quantum mechanics that you can actually measure. And you can actually, and it's really the ground state, really matter organize itself to be all these, let's say, state at the same time. And you can even scale up the system and create the gas in many different configurations. And I would like really to conclude, because sometimes I think on the one hand there is this beauty of many-body quantum system and thinking, okay, we discover new type of phase of matter, but maybe one can wonder for what we really can use it. And here what really is a powerful concept is this universality that sometimes you find in physics. And indeed, the physics that we are touching with this new phase of matter, which is called supersolid, is the physics of modulated superfluid. So a superfluid that is breaking the translational symmetry, building spontaneously pattern. And so, and this is actually, we are discovering now that this is much more general than expected. And I would like to give you an extreme example of how general this type of phases can be. And indeed, there is a connection which we were not aware and that we are still, let's say, investigated between creating extremely cold quantum system in the lab of 100 nanokelvin temperature. There is a connection with neutron star. Now, neutron star, I'm not a specialist at all on neutron star, but those are amazing objects. So imagine that you have an object which is much smaller than Rome. And in an object much smaller than the city of Rome, you can put the mass of the sun, or even bigger than the mass of the sun. And imagine an object that at the same time so heavy, so extremely density, is rotating continuously, and you do a full rotation in, let's say, milliseconds. It's kind of, let's say, radio sources. Those are our neutron stars. And now the neutron star, the way, let's say, its thought to be made have a core which is liquid, an outer crust which is solid, the core is liquid, and actually is cold enough to be a superfluid. And in between the two, there is this inner crust that is both crystal and superfluid at the same time. So very reminiscent of the state that we call it supersolid. And what happens in neutron star is that since the pulsar are emitting light continuously, they also lose energy. By losing energy, they slow down their rapid rotation, and you see here in this loop is just the rotational frequency going down, 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 but then sometime, without that it's really clear why, there is, boom, a glitches. It's slow down, slow down, slow down, and at some point, boom, the neutron stars slow up and then slow down again. And there is many theories on where these glitches appear. And one of the theory is that actually, but in this rotation of the superfluid, you create vortices. The vortices unpin from the supersolid part in the inner crust, and the vortices itself, they crash in the outer crust. And so, and this is these little glitches, which is really very little. Something we, for example, wanted to test in our laboratory. So now I'm showing you, let's say, a simulation of a supersolid that we do at ultra cold temperature in our system. So you will see on top there is the residuals, and below you have all these black dot are vortices. And so now we are putting our supersolid in rotation. The supersolid has many vortices. We have created all these vortices. And now let's see what happens. And you see that, so here's where you can highlight. You see that when a vortice is escape, you have these little glitches appearing, very much reminiscent of what is in neutron star. This is an example, and I think there is much more that we can learn on how to build connection between fields which are so diverse, and how the specific control that we get at the many body level on ultra cold atom can really help to kind of identify possibilities and theories in much more complex systems which are not directly accessible to humans. Thank you very much.